We got it. Do I need the mic? Yeah, I probably do, huh? Okay. So hi, I'm Karin. I am from the University of Melbourne. I am from the School of Computing and Information Systems at the University of Melbourne, as well as the Health and Biomedical Informatics Center. And this is actually a reprise of a talk that I gave with my colleague James Bailey, which is why his name is there, at an event called the Convergent Science Network, which is a public lecture series that is run around Melbourne. If you're interested in kind of the intersection between biomedicine and computation and engineering, that's kind of an interesting one to attend from time to time. Okay, so I'm really happy to be here giving this one again. You guys are probably a little more technical than the audience I was assuming for my previous talk. So, you know, if you want me to talk about anything more depth, I guess just let me know. So, before I get into kind of machine learning, I'm going to take you on a journey to someday in the perhaps not too distant future. On this day, you are feeling unwell and you decide to make a visit to your doctor. You arrive at the medical center and are taken immediately to a small room. In this room, you're greeted by Dr. Digital. Dr. Digital is a specially trained computer program that has been designed to conduct patient interviews, including taking of your history, a collection of a range of physical examination variables that are collected through devices in the room, like a blood pressure cuff, a smart scale, a glucose monitor, a stethoscope. These devices can transmit their measurements directly to the doctor. Dr. Digital also has access to your whole medical record, and he knows what diagnoses and treatments you've had in the past or that are ongoing. He begins the interview by asking you what brings you to see the doctor today in a pretty normal way, and you explain your symptoms. Dr. Digital takes all of this information in, relates it to what's in your medical record, and begins to form a hypothesis about what is ailing you. He instructs you to place a stethoscope in a specific location over your heart, guided by a projection of a skeleton over your body, an augmented reality tool that signals to you exactly where to put this chest piece. The sounds that are picked up by the electronic stethoscope are converted into a digital form after filtering and amplification, and are sent immediately for analysis by one of Dr. Digital's built-in algorithms. This cardiac algorithm can detect different kinds of murmurs and various heart disorders from the acoustic signal. The algorithm classifies your heart sounds as abnormal and alerts Dr. Digital to a high-confidence diagnosis of pulmonary stenosis. Dr. Digital uses this information to ask you several follow-up questions, guides you through taking of several additional measurements to rule out alternative diagnoses, and finalizes your diagnosis. Next, Dr. Digital scans the current clinical practice guidelines in the literature, searches for relevant clinical pathways that you should be put on to guide your care, and reviews the latest research for additional advice on treatment options. Finally, Dr. Digital calls in the human doctor overseeing the practice, Dr. Smart. Dr. Digital summarizes the information that has been collected about you, explains the diagnosis that has been inferred and the reasoning underlying it, and presents the treatment options with an assessment of its highest confidence recommendations. Dr. Smart reviews this information, checks for any mistakes or anything Dr. Digital overlooked, confirms the diagnosis, and then discusses the pros and cons of the treatment options with you. You come up with a plan for next steps together. Okay, so in this scenario, of course, there is a human doctor in the loop. So I guess I should preface everything I say by saying I'm not trying to argue that AI is taking over the world. So, all right. So what is inside of this digital doctor? Let's take a look. All right, most fundamentally, Dr. Digital consists of data and algorithms that make use of this data for various tasks. The data that's relevant to the clinical context can include everything from patient-level characteristics, the results of laboratory tests and investigations, right through, as I mentioned, to the research literature that provides the evidence base for helping the doctor make decisions about diagnosis and treatment. And in a few minutes, we'll talk a little bit more about some examples of how we can use machine learning algorithms. And so I will jump right in. So just a little bit of background on what machine learning is. Okay, so how many of you already know what machine learning is? Most of you, cool. So I don't have to spend too much time on this slide, which is good because then I can move on. But anyway, basically, when we think of machine learning, we think of algorithms that know how to make use of data and apply those algorithms to infer a model to solve a particular problem. And the basic setup for machine learning, as those of you who know what it is already know, but for those of you who don't, is to look at historical data. So basically look at examples of some solution to an existing problem, apply machine learning in order to build a mapping from those examples which relate the input characteristics of the data to some particular task that's trying to be solved. We build a predictive model, and then the idea is that in a new scenario we can basically treat that as a question, run it through our model, and have an answer at the end of it. So an example of this sort of thing might be to try to predict readmission into the hospital. So somebody was in hospital for a while and then got sent home. Can we predict how likely they are to be readmitted to hospital within a 30-day period from their discharge? We might consider historical data, right? We can look at examples of lots and lots and lots of patients and capture as much data as we can about those patients, demographic information like their age and their gender, but also their actual clinical data, so laboratory results, whatever measurements we've taken while they've been in care. And then we critically need to know whether or not those patients were readmitted within 30 days or not. That provides us with what we call labeled data, so basically examples of patients that we know have the problem that we're interested in modeling. So in this case, we're interested in trying to predict whether a patient will be readmitted within 30 days. So that means we need to look at patients that were admitted within 30 days in our historical record to find those examples. We also critically need examples of patients who were not readmitted within 30 days in order to be able to build a model that can discriminate between the patients that are readmitted in 30 days and those that aren't. So once we have that basic data, then we can run it through a machine learning algorithm which will effectively try to identify the combinations of factors that are predictive of that 30-day readmission. And so what we're doing is essentially deriving a formula which weights those different factors. And all together gives us a probability of that 30-day readmission. And so it might look something like this. Obviously, I've cut off most of the factors, but maybe it's 0.03 times the person's age, plus 0.07 times their white cell count, plus some weight on some other laboratory result, and so on and so forth. That's the basic approach that we use. Are you confused by this? Questions? Yeah?
Why is that only a linear formula?
Well, because I'm trying to keep it to be a simple example.
But it could possibly have things like sinuses and logarithms or something.
Yeah, so the machine learning algorithms, there's a whole bag of machine learning algorithms. In fact, we'll get to some of them a bit later. So I'll take that on hold and we'll come back to it in a minute. So the basic requirement of applying this kind of machine learning approach is lots and lots and lots of data. And specifically, we need lots and lots of examples of the problem that we're trying to make predictions about. And so when we have small data, this is bad. When we have big data, this is good. We can build more robust algorithms by considering more and more examples. And just to make the point that there's already a lot of machine learning in our world. So trying to think about applying it in the healthcare context is just sort of a natural step from what we're already doing. So Google, Facebook, even the grammar checker in Microsoft Word makes use of machine learning under the hood. Google Translate is probably the most successful application of machine learning that's out there today. They're getting better and better all the time, and if you believe the latest research coming out of there, they can translate better than people can. I don't believe their research necessarily, but anyway, this is what they say. All right, so to your question, what kinds of algorithms can we have? Yes, I showed you a very simple linear regression model, but actually we have a whole bunch of different kinds of algorithms that we can try to explore. One of the common ones that are used is something called a decision tree, and obviously I don't expect to be able to read that fuzzy print you can't see, but the basic idea in a decision tree is that we consider particular factors and we look at the value of the particular factor, and depending on what the value is, we go one way or the other, and then we look at the next feature, and basically we have, like it sounds, a set of decisions that we make until we can arrive at a prediction. And this is actually a very common approach, and it turns out that when we take thousands of decision trees together and allow them to explore particular combinations, different combinations of different orders of looking at the features, we can infer a model that's really good. That's something called a random forest model, and it basically is a collection of trees that look like this. So if patient has plasma equals some value and age equals some value, reading down this decision tree, then the risk of death is high, or the risk of recurrence in 30 days is high. So that's one class of models. Another class of models that we hear about in the news a lot these days is deep learning methods. So deep neural network models are very, very different from linear regression models. They basically involve having layers and layers and layers of nodes, and somehow our input representation gets mapped to an output representation by squashing variables in various ways, and these are completely uninterpretable, and nobody actually understands the models at all, which is a total contrast to our decision trees, which you can read right off. So if you're a doctor, we got some doctors out here, I know that. Which one would you like better? A model that you put stuff in and you get stuff out, and you have no idea what happened in the middle? Or a model that you can get some explanation for the decision? Yeah, the last one, the first one, the top one.
When you go really to be a doctor, sometimes he makes decisions he cannot really ask why he comes to the decision.
This is true. So doctors are, first of all, not perfect. Doctors are also biased. Doctors cannot sometimes explain their decision making, but nevertheless, doctors really despise black boxes. Okay, so the basic point here, yeah.
So I just had a question about the interpretable tree. Is that automatically dynamically running through, or is that set?
The structure of the tree? So there's a statistical algorithm that's kind of buried in here, which basically requires the algorithm to identify the factors which are most predictive of the output variable that we're interested in. And the size of the tree depends on various parameters of the algorithm. For instance, there might be a threshold. So if you get a certain level of classification accuracy by looking at 3 factors, then you could stop. You don't have to keep looking at factors. And that's obviously a parameter that you can set, sort of like what level of accuracy are you comfortable with, so that you don't have to keep exploring that space. But every time we make a decision, we're really only, from that point forward, considering a subset of the data, because they're the ones that satisfy, if patient has plasma equals some value, if it's, let's say, greater than a certain value or less than a certain value, once we've decided that, okay, this patient has plasma greater than whatever that value is, we're only looking at patients that have the value greater than that value, whatever it was, and we're trying to look at the factors that are relevant for that subpopulation. Does that help?
Yes.
Okay, so decisions that we're trying to make often involve predictions. So when you're driving on the highway and you're trying to decide the best route to get from your house to your work, you're making a prediction about where there's going to be less traffic, where if you get some additional information, like there's a traffic jam on the Eastern Freeway, you might use that to make a prediction about which outcome is the best for you, which choice is the best for you. So every time we're trying to make a decision, we're really making a prediction about different possible outcomes. And so that's really the point here, is that when we build a predictive model, we can use it to help drive decision making. Okay, so what is the scope of this kind of machine learning approach? Really, it requires us to have a very well-defined prediction scenario, because we have to be able to build those labeled training data and collect the labeled examples in order to build a model. The model has to be predicting something, and so we have to define what that something is. Admission in 30 days, or admission in 2 months, or does this person have breast cancer, or do they have colon cancer? If we're trying to make a decision like that, then that we can build a model, because we have a very clear task that we can translate into sort of the machine learning representation, or really a mathematical representation. We have an input, a set of input features, and we have an output variable, and that output variable has to be well defined. The machine learning algorithms, I don't know what that was, but anyway, the machine learning algorithms are excellent at discriminating between clearly specified outcomes, and where they are less well specified, the algorithms start to have trouble. And so that means that in the context of current applications, we really need to avoid loosely defined data sources and outcomes. A question like, why did the patient visit today, is a very open-ended question, and it doesn't have a well-defined outcome. It doesn't have a well-defined target variable, and so that's not the sort of task that we can address with a standard kind of current state-of-the-art machine learning algorithm. Something even like, is the patient seriously ill, also is a very general kind of question. What do we mean by seriously ill? And unless we can define that in a more specific way, we really can't collect the kind of examples that we need in order to allow us to build a meaningful machine learning model. Okay, so why would we want to use machine learning in this kind of context? Well, hopefully it introduces some efficiency into the clinical treatment process, so it might free up our clinicians to do other tasks that require them to apply their knowledge and their experience, and maybe engage a little bit better with the patients. In my scenario, having Dr. Smart discuss different treatment options and that sort of thing is really, really important for the patient experience. It also hopefully allows us to build slightly better predictions, which are not as susceptible to the kinds of biases in the doctor's experience that humans can be susceptible to. There's recent research that shows, for instance, and this one I actually believe, that machine learning-based algorithms are now able to analyze potential melanomas more accurately than people can, than the pathologists that look at those images. And why is that? Because they're actually in the case of an individual pathologist or an individual analyst, human, they have their one set of experiences, but the algorithm has thousands and thousands and thousands of examples of solving this problem, and so is able to abstract in ways that the people can't. We also can get quantified predictions, which is not something that people are particularly good at. You know, what is the probability? Oh, there's a 0.8 probability of something happening. Really? Okay, how did you derive that? Well, the algorithm can do that based on the examples they've seen in their training data. It's not something people are good at, right? And of course, they can consider a larger number of possibilities in the search space than what people can handle. You know, there's ideas from psychology that we can only kind of keep 7 things in our head at one time. And so, you know, a computer has no such limitation. Okay, I'm running out of time because I have too many slides. But I'll just talk about a few examples of things that are happening. So I already mentioned the melanoma prediction from images, and I said on par here, but actually the data suggests that the algorithms are doing better than the human experts. There are other examples. For instance, in the radiology space, the computer can predict with about 97% accuracy based on an image of a bone, whether or not there's a fracture there on the image. And similarly for breast cancer, we're now seeing the algorithms coming pretty close to human capability. And when you combine a human and a computer, it's even better. Another application that my colleague James has been working on is in the space of virtual surgery. So actually using machine learning to provide feedback during training of doctors. So allowing them to manipulate in a virtual environment and practice their skills and get feedback from that prior to their actual cutting up of people. This is useful. I work a lot in the text space, so my background is actually in natural language processing, and so I'm trying to do as much as I can on trying to analyze clinical text. And what we're trying to do here is to take something like this, which is a discharge summary of a particular patient, and try to identify the kind of key concepts that are represented in this. So there are things in here that we can recognize as kind of important clinical information. We have some demographic information, 68-year-old female. We have some more clinical symptoms that are represented. So we have shortness of breath, we have cough, and then we have information about lab results. Her D-dimer was positive. We have dyspnea here, which is the same as shortness of breath. We can make sense of that if we know that, and we can capture other things: constipation, anticoagulated, and so forth. So we can, by looking in the text, we can actually dig out kind of that key information. And so one of the things that I'm trying to work on is actually trying to use machine learning to help us do a better job of structuring the information that's in these clinical texts. Now, we want to go beyond those concepts and actually understand relationships. And in fact, in this particular example, one of the things that's really important is the progression of the patient's illness. So there's information here that the patient progressively was getting worse, and that her shortness of breath was coming on with any kind of activity. And that is actually quite nuanced level of information. It's much deeper information than you would expect to be able to put in a drop-down box in an electronic medical record. We can't really anticipate that information, but the clinician notes it and writes it down, or typically dictates it actually. But once the information is there, we want to be able to use that information to help us build a better model of what's happening with this patient. So there are some applications where we've been trying to use this actively. So we've been working with pathology reports around tumors to try to structure the information that's in those texts. Again, you can't read any of this stuff, but anyway, this over here is a pathology report, and this is actually a structured representation of the key facts, in particular the tumor stage information that's captured in that report. Another kind of application is in infection surveillance in hospitals. So patients get sent off for in this case, CT scans for suspected lung infections, and those results come back and they sit in a pile until somebody actually picks up the piece of paper and reads it. And so we've been trying to basically apply natural language processing techniques to flag the reports that have evidence of a positive fungal infection, so that those patients can get treated sooner rather than later, because it's really life or death. The earlier you start treating them, the better. And we've been working on actually trying to identify patients that have particular diseases in a large data set. This is work we've been doing with the Alfred Hospital. And we found that by combining all the structured information that's in the record along with the unstructured information like pathology reports and radiology reports, we can do a much better job of finding particular kinds of diseases. So when we're interested in finding patients that have lung cancer in our database, we can do this by using machine learning strategies. Yes?
Is the fact that you're trying to create a common structure for all of your diagnoses, is that a cause for why sometimes there are some urgent cases which are not able to find immediately?
Urgent cases that we can't find easily.
Yeah.
What problem am I solving?
Because at the moment you have forms there which are very generic, right? And you have the same form for all kinds of patients, whether they are in a critical condition or whether they are in a normal state, right? So the fact that you have very generic forms, is it causing the delays when you're not able to find exactly immediately which ones need attention?
So it's not the forms that are causing delays, right? So actually this is helping us, because we're taking, it's when the information right now is in text, and so that is actually a lot harder to deal with. So converting it into a form means that it is more accessible. Once it's structured, we can flag whatever, right? So if when we analyze the text, if we work out that there is somebody who at that case, it's, if they have tumors stage 4, then they can send an urgent message to the clinician and say, this patient's really ill, do something about it.
It's able to help you.
That's what we hope. Is this actually used in practice? Well, that's an IT problem. Okay, so just quickly, another kind of thing that we're trying to work towards is something that I like to call patients like mine, which is the idea that when a patient comes into your clinic, you can interrogate the whole record of patients that you might have access to in your hospital or possibly in the whole world. That would be fantastic. So that we can first of all try to understand how different groups of patients, what they have in common. And so if patient comes into your office, let's say it's Miss Orange, and Miss Orange is just another patient, you can try to work out what other patients in the record are similar to Miss Orange, so that you can then examine how those patients might have responded. These patients here, all the purple people, how they might have responded to particular treatments or what diseases they are known to have. And so this allows us to do something which my friend Nigam Shah from Stanford has called the green button kind of approach to medicine, where in a given clinical situation, we can look to see whether there is a guideline that addresses that clinical situation. Great, if there is, use it. More often than not, there won't be one, because your patient won't match exactly the known criteria for a given guideline. And so then we can go into that medical record database, find the patients like mine, and identify those similar patients, and really do some analysis and prediction on what kinds of treatments are likely to most benefit Miss Orange. So we can use that concept to make a decision. This really requires having lots and lots of data. I might stop there and just say that some of the issues that we're dealing with in this space really are social issues and cultural issues. So we have a lot of concerns about patient privacy. We have a lot of concerns about interpretability of algorithms. As I said earlier, the doctors don't want a black box. We also have lots of challenges on the machine learning side. So it's easy for me to say just throw lots of data and throw lots of examples at it, but actually real-world medical data is extremely heterogeneous. We have all different kinds of information. We have symptoms, we have demographic information. Eventually we're going to have genotypes as well. We're going to have genomic information. We have behavioral, we have environmental, we have, Fitbit 24/7 data. We have all kinds of data that are potentially relevant to helping us understand people's health. That causes a problem from the perspective of modeling because that's a whole big, complicated feature space to explore. And I'm not sure our algorithms are really up to that just yet. Certainly deep learning algorithms, that kind of complexity of data, you'll probably be running those algorithms for about a month and won't get a result. So it's really, there are still some open questions in terms of applying machine learning in this context, also because there's a lot of variation in how much data we have about any individual patient, and so, how do you match patients if you have different amounts of information about them? Interpretability is a really, really big issue, and so we need to consider that in this context. And specifically, I just thought I'd mention that in the European Union, they've recently passed a regulation that will require that all individuals can have a meaningful explanation of the logic involved when there is an automatic screening or an automatic prediction tool that's applied to them. Now, this has huge implications for how we use machine learning in the medical context. Okay, I will stop there. Is there anything else that's actually interesting? No? Good. Thank you.